Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. We're just starting in on level layout stuff, laying out rooms in our game today. We're just getting started. We don't really know much about how this stuff's going to work or what we're going to be able to do here. But we wrote some code that just does some simple stuff with level layouts, and we're kind of trying to get to the point where we can see what we can reasonably do with procedural generation of how rooms are laid out and so on. Much like the lighting algorithm, we're not going into this with any preconceived notions. We're just trying some things and we're going to see what happens. And later on we may take a look at the literature as well and see what we can learn from that and integrate that into what we're doing. But at the moment we're just trying to get our feet wet and see like what we like, what seems to be the right set of utilities for something, and how it goes. All right, so let's go ahead and see where we left off. If you remember from yesterday, we had gotten to the point where we actually had a sort of a full system sketched out for doing some size computations. And we just finished it at the end of the last stream, so and we were overtime because you know, I didn't want to keep dragging it on, make the stream too long. We didn't actually get a chance to run it. So where we're at right now is we're at the same place we were yesterday because we if-zeroed that code out, but we changed the way that rooms are defined to match the way that we think we're going to want to. So again, same place, starting place as yesterday, but now we've got all this code in there that we can now turn on. And so what we want to do is turn that code on and then try to get it to the place where it's sort of working and we can start playing around with it. So I'm going to go ahead and remove our if-zeros. Here's our code, and there's a couple things we have to implement. There's a stack thing that we made that we were using to sort of track rooms as we crawl out along the network of rooms, and we want that to sort of be our little utility we can use whenever we want to crawl rooms. So that we didn't implement. We never quite got there. So we've got a couple things like that that we want to implement. So for example, this push room call is the thing that puts something onto that stack, right? And so what that wants to do is that's just going to take a room, and if you remember correctly, this stack is just real simple, right? It's just a thing that says, oh, I've got a pointer system memory arena that I can just dump things onto, and I'm just trying to keep track of what the stack is. We also know, right, that we had the pop room version, so we know we've got both the push and the pop that we want to do. And so let's just put those both in here and write them both at the same time. These are just crazy simple, right? There's nothing interesting about them. We're literally just making a simple little stack here. And so if we want to write the straightforward version, we just say, well, we know that there's a room stack entry that gets generated every time we push. So we just say, all right, we want one of those. Of course, we have a free list, so we can just do first free. If it turns out that there is something on the free list, we take it, and we're pretty much done. We just say, okay, the first free is now the whatever comes after this one in the free list, and off we go. And that's all we have to do to get one. But if we don't have one, then we need to allocate one. So then we would end up in a situation where we'd allocate it. Now, what I can do here is sometimes when I don't like to write it this way sometimes. What I'd rather do is make it so it always succeeds. I think this is just a little more fun and a little easier to read. If I just say, look, if there isn't one, let's just put one on, right? So if there isn't something on the free list, then I'll just do a push struct using the memory that I've got, and I know that I want one of these gen room stack entries, right? And that gets me something on the free list. So basically saying, look, let's just say we always get it out of the free list and we just know. And so we always do this exact thing every time that we do it. But instead, we're just gonna, seed the free list with a available thing if there wasn't one on there to begin with, right? And so that's just an easier way to write that, in my opinion. So I tend to write it that way fairly often. All right. So now, once we get on, once we actually have the thing we're going to fill out, we know we've got entries here, and we want to basically put a room on that. That's the thing we're trying to store. And then the previous entry is whatever was behind us in the stack, right? And so we know what's behind us in the stack because we've got the stack top pointer. So we know that the top is what was there. And so we just want to go ahead and replace the top with ourselves. And so this is just creating a backwards pointing list that just as the stack goes, it just pushes stuff back there. So then once we need to pop a room, again, really, really simple here. If you've been watching Handmade here at all, hopefully this is just a no-brainer to you and it's very simple. If you don't watch Handmade here that often, maybe this is just like, whoa, I don't know. I just, I just used something from the STL. I don't know what a stack is. Okay, no big deal. It is not scary, right? All this thing is, it's just a chain of pointers. That's it, right? It's a pointer to the top, and each one has a pointer to the one that was before it. So if we want to find out what the thing is on top of the stack, we know we can get that really easy. We just say, okay, the top comes from stack top, right? And right now, we don't really need to do it this way. If in the future, I'm going to leave it like this, just because if in the future we want to get multiple things out of it, we may want to do that. But really, all we need is the result here. And so we can really just say that and get all that we were, all we're going to do is pull that room out and then return it. But you can imagine if there was more data in here eventually, we would want to maybe snap a pointer to it. So, 6 of one, half dozen of the other, but that's roughly the way we want to do it. Now, well, you know what, here's what I think. Probably we should just assert on failure when you try to pop the room because we have a check for it. I'll let you, you know what? Let's do it this way, and I'll let you try to pop an empty stack. I'll just let that happen, okay? And then there's a good reason why we put the top on there, right? Because now we're gonna check the top, and then if the top has something in it, then we get it, right? And so that seems reasonable because then, off we go. So anyway, once we get one of these things off the stack, we're not quite done because while we have given you what the room was that was on top of the stack, we have not popped the stack. And this is called pop room, which means it should take the top thing off the stack so the next time someone looks at the top of the stack, they're going to get something different, right? So what I want to do here is say, okay, we know that now whatever the top pointer is should be the next thing. Right? We want to move it down the chain. And furthermore, we don't want to lose that piece that we've got. We'd like to recycle that memory the next time you try to push a room. So in addition, we can just take the first free and remember that by saying, oh, whatever the first free thing was that was on there, its previous, I'm sorry, whatever the first free thing that was on there, that can be our previous. Right? So basically, whatever the thing was at the top of the first free list, which again is just this big long list of pointers, are going to freed ones of these. Let's just remember what that was and then stick ourselves on top of the free list, right? So this basically, really what pop room ends up doing at the end of the day is it's just managing two lists. It's taking off one and putting on the other, and push room is the exact opposite. It's just, we're just cycling between, we're just moving things from one list to another, right? So this way, we never take more memory than we absolutely need to, because we're always going to just recycle something if we had a free one available, right? We can just stick it back in there. All right. So again, let's just go over those really quickly now that you've seen them. So when we do push room, we say, look, is there anything on the free list? If there is, then great. If there isn't, what we need to do is add a new one. So we use the memory point, the memory arena that we know we're supposed to use. We just make a new one. And again, this will clear to 0. So we know that it comes through as all zeros here. Not that it matters. We could tell it not to clear, in fact, if we were cared about the speed. You could do this. I think we've got... right, we can just say don't clear. And that way we won't waste the time because we know we're going to fill out everything in here. So we could do that too. It's up to us. So we come in here and we say, all right, let's add something to the free list. We don't have one. We then get the thing off the free list, which would either be the one that's just been there, or it's the one we just put. And it depends on whether there were any free available, right? So then we say, okay, after we grab that one, we want to advance the free list one forward. If we just added one, right? Oh, well, I guess you know what? That is a reason why we would want to clear it. Right? Because we need this pre-pointer to be 0. So we might as well let it clear if that's what we wanted anyway. And hey, we're clearing this a little bit much, but romping zeros is probably best in this case anyway. All right. So off we go. We look at the first free, we grab it, we move the first free to the next pointer. We've got the room here, we record which room it is, we got the prev pointer. We say, all right, the previous thing is whatever was on the top of the stack, and now we're at the top of the stack. Done. For popping room, same thing in reverse. We say, all right, what's at the top of the stack? If there was something at the top of the stack, we do it, otherwise we don't. Now notice the structural difference here. Why is there a structural difference here? The structural difference is because push room must succeed, right? Anytime you push a room, we must succeed. So if we need more memory, we'll get it. Pop room just doesn't do anything if there wasn't anything on the stack, right? So we want an actual if around the whole operation, because if there was something on the top of the stack, we don't do anything. So that's the difference. Everything else is the same. We take the thing off the top, right? We say, all right, let's take whatever the thing was that was right before this one that had previously been the top of the stack. That's now the top of the stack. And then we also say, all right, whatever the thing is that we pulled off, which is this top, right? I don't like, you know what? I don't like the fact that it's called top, because it's not the top anymore. How does that look? Better? So we pop this guy that we're gonna remove off. We say, okay, get the popped room, that's the result. The stack top is now whatever we popped previous, so the one that used to be on the top is now on the top again. Our previous becomes whatever the free list is, and the free list points to us. Done, right? Now, if we wanted to, we could also fill the room with an invalid pointer, right? So, like, if we wanted to, we could do this. And that way, if somehow you tried to use it accidentally, you would know, you'd fault, because you'd be like trying to look at zero memory. So we could do that as well. It's ineffectual because in any well-working version of the program, the only person who ever writes to it is here, and this is always non-zero. In fact, we could ensure that's true. We could ensure that's true here as well. So, we can add a little layer of carefulness there if we want to. We don't have to, but we can. So that's our push and pop rooms and how those work. Now we can finish the rest of the stuff that needs to be there. So let's see. We have the room stack there. That's fine. All right. And so now we get down into the place room stuff that we were looking at before. And we seem to have some parentheses problems here. And there was too many of them. There we go. Okay. There we go. We also got some, these are supposed to be pointers, looks like. And we did not do that properly. Go. Let's just get that fixed there. All right. And so now we're back down to, like I said, just the couple things that we need to do here. Looks like stack probably needs address of there. So now we're back down to the functions that we wanted that we hadn't actually typed in yet. And so what I'm going to do is actually break those out here. So can be direction is going to be stubbed at the moment. So and we could actually just go put this in for real, I suppose, which is originally when we wrote the stub code, when we said, here's the rooms, here's how the rooms are connected. What we didn't specify is which directions those rooms were allowed to be connected. So for example, all connections would be allowed to be staircases up and down. In the current system, because all you say is this room has to be connected to this other room. But that's realistically not what we probably want for game design. For game design, it makes a big difference whether something is connected up or down or not, because they feel different and they have different implications to us in terms of our mental understanding of the world. For example, a forest cannot stack on top of a forest. Not in most cases anyway, right? So the player would perceive something odd if you had a forest with a stairwell and a forest on top of it, right? So depending on the type of room that it is and the way that connection is supposed to be played out, we oftentimes will want to restrict connections to either up and down only, if it's like a bunch of rooms that are supposed to be stacked on top of each other, or sideways only. So most connections are probably going to say either I can be north, south, east, west, or I can be up, down. Most will not be both. And so that was the thing that we sort of realized when we were typing in the actual room connection code. And so that's why we want to be more specific here, right? So we want this directionality to be respected in that sense. Right now, what we're going to do is just kind of leave it blank, I think, and then we'll take a look at that in a second. But we also have to deal with has entries, which is the way you tell whether or not the room stack has anything in it. And we already really, we know exactly what that's going to look like, right? Because, oops, hit the wrong key there. If you don't hit the wrong key, then what you can see is that the stack already has the code for whether it could pop. It's this right here, right? If the stack top pointer points to something, then it's got entries. If it doesn't, it doesn't. So the answer to whether a stack has anything on it it can push is pretty darn simple. It's just whether or not this is a valid pointer. That's it. Make sense? Okay. So now we've got everything in there, and we just need to deal with our concept of direction. Now what I want to do to deal with this concept of direction is I'm going to pull this function up a little bit, and I'm just going to talk about this in terms of how we actually connect rooms. So if we go over here and we take a look at room connection, what I want to do is introduce a mask here, or a direction mask, I guess I should say. And I'm going to sort of have an idea of what these directions should be. And I'm going to kind of talk about them semantically as well. Now, if I remember correctly, we've done exactly this thing before. Exactly this thing. And where we did it was we had this notion, and I don't remember exactly what it was called, but it was basically like a thing that lets you get a box sides. It was for the lighting. Surface index. That's what it is. It's this thing right here. So if you remember this thing, it had like a surface index, right? And the surface index was decrypted in this fashion. And so what you ended up saying was like, okay, I pass in a surface index, the axis and the positive or negative are like interpreted this way. Well, I'm a big fan of just once we have a way to do something, let's keep doing it that way unless we have a real reason not to, because chances are if there was a reason we did it that way the first time, there'll probably be a reason to do it that way this time. So what I'd like to do is come up with a way of sort of abstracting this exact behavior, and then we'll just use it in both cases, right? So we'll have this notion of what a direction is, like a box, surface mask or something like that, and we'll grab this out and we'll make this be sort of our definition of that, right? And that way well, you know what? I'll just do it like this. All right. So this will tell us essentially what we mean by these things. The axis in this case is the x, y, and z, and it's positive or negative, which way it's pointing, right? And so we might want to give a little more. I don't know. Anyway, point being, if we just stay consistent with this, then this is the information that we actually want to know, which is axis index and positive. And so what we can do is make something that translates to and from that. We can basically make a struct here which encapsulates those two things, for example, and we can return those when you actually want to know what they are. So for example, I can say box surface parameters, something like that. Right? And what we can do is say box surface parameters and you just pass the index, and back come these two. So that's a way to go, Jimmy. That's a way to go sort of in, and we need a way to go out, right? Maybe we'll call this out, and we need a way to go in, if you will. So what I want to do is make a way to do get surface index and pass the params, right? But really, we probably don't need to bundle them. We can probably just do it like that. And then, oops, I don't know why I typed I. Then what we can do here is just say, we know how to produce one of these. We just say that we do the opposite of what's going on here. So positive, we assert positive is less than or equal to 1, right? I mean, another way to say that would just be that it's equal to 0 or 1. And then axis index has to be less than or equal to 2, because it's 0, 1, or 2, right? And then the result is just going to be the surface index shifted up and ORed. So that's a way to go in and out of this thing. For what it's worth here, right, I can do this. And now that's using the same code, so I know that it's consistent, right? So that's really all I'm talking about there. I'm going to go ahead and pull these in here. I don't know really where we want to put that. We could choose to put stuff, sort of wrap it up into its own thing at some point if we want to, but I don't know. Anyway, the box surface mass that we have here, we could call these names as well. So if we think about what these are, x-axis negative is like west, x-axis positive is east, y-axis positive and negative are like north and south, right? And z-axis positive and negative are like down and up. So if we want to, we can think about these in that way, and these are these are sort of the individual indexes that make up what we're talking about, right? Now, the problem with them is we have two ways that we want to refer to them, and so we have to kind of think about how they will end up in a mask. These produce indexes where 0, 1, 2, 3, 4, 5 are the 6 directions we're talking about. But if we wanted to OR them together, we would need to generate masks out of them. This is... I kind of just want both. So let me do it this way. Something like this. And the reason that I'm doing this is just because I want to be able to refer to both of these things quickly and easily. And they're two different things, right? So one is a surface index, and those are the actual values. The other is the mask, and that's just the index, whatever it is, right? In mask 4. So do you see what I'm doing there? One is just 0, 1, 2, 3, 4, 5. The other is one shifted up that many places so that I can OR them in, right? Very, very straightforward. But it allows me to kind of like play with that and figure out what's going on there, right? So what I want to do here is say, all right, west, east, south, north, down, up. And at this point, this is getting ridiculous enough that I think I may just go ahead and make handmade box. You know what? Let's just go ahead. Treat yourself to a fresh file. And then I can just put all this stuff in there. Oops. There we go. And I can put those world-gen functions in there as well. There we go. And now we can look at light box surface and pull that in. And now this stuff is kind of all just in one place. And we can start to build up more things about this as we want as well, right? Yeah. All right. Excuse me. So hopefully this all makes reasonable sense. Now we've got the ability to talk about all these things. And I will go ahead and add them to the Handmade hero list of include files that we use. And you know, this is probably a pretty easy generic thing. So it probably should be pretty high up on the list. What does it say? Oh, got a semicolon. All right. So now that we've consolidated that stuff in there, and that's all pulled out into a nice little box file that we can use to do stuff with boxes, and we probably will want to do some other things with boxes in the future, right? But this is just a nice way of like summarizing our notation. So if anyone wants to know how we're talking about boxes in any part of the code, they can just look in here and it's pretty clear how it works and what it does and why, right? And furthermore, here are the functions that you can use on it. Nice and easy to read, right? And I do like that stuff. So you notice on Handmade Hero, I don't fetishize any of those sorts of things, and we never do it earlier than necessary. But once I'm obviously at a point where I'm like, this is how we're talking about stuff, I do like to bring things out and sort of pretty them up and make it so that it's nice and like, all right, we know that's how that happens now. Off we go. So let's go ahead and take a look at dir mask. So here's the dir mask. What I want to do is say, all right, the connection dir mask needs to be set for whatever the surface index is. What's the surface index for this thing, right? Well, now we know. We can just say get surface index, and here we go. We pass the axis and whether it's positive. So there's dim inside, and then that tells us, and we're done, right? So that's pretty handy, and it's really, that's it. Yeah, not much else to it. So that's all good. This, of course, doesn't actually need to be any specific size, I suppose. So in here, our can be direction now works. Unfortunately, our code would not work at all now, even if we didn't have any bugs in the stuff that we've wrote and never tested, which we kind of need to start testing now, certainly. But this basically means we could never lay out any rooms at all. The reason for that is our connect function has no idea what to do. right? It's putting in a 0 for that dir mask, and because it'll just be cleared. So that means the direction can't exist in any way. And so what we need to do here is start actually specifying what the dir mask is when we connect rooms together. Now what we can do is, by default, we can say a particular thing that should be the general mask, which is whether we want planar or I guess vertical motion, I don't know. But we can see that we've got a planar box mask, which is just going to be, you know, box mask west, east, south, and north combined together. And that's our planar mask. And then we've got an up and down version. And I guess one thing that's a little confusing about this is really the direction mask has to be stated relative to somebody. So suppose you wanted a connection where A was on the bottom and B was on top. Well, if I just say box mask up, that's not really what that means, because how did you know which one was supposed to be the up, right? So we probably want, now that I'm thinking about it, to make the name of this more explicit. So mask on direction from A, or like direction from A mask. Because you can, it's always symmetric. So when you specify one mask, we know what the other person's mask is, right? Because if you say that this can be west or east, then that by default means that the other one could be west or east, whichever the opposite is. If you say it's only west, then that means the other one had to be only east, right? So we kind of know that they correspond. So we don't need to specify both. But we do need to say specifically which one we were specifying it for, because otherwise it's very ambiguous to someone coming along and looking at this code. What do you mean direction mask? A thing goes in two directions, right? So in a sense, we need to be able to specify, and again, we don't want to specify bilaterally directions, because we do want to say, did you mean up or do you mean down? We need to know relative to a room, though, first, right? It goes up from A. So I think it is roughly what we want in that case, but we do kind of need to be able to obey it a little bit more specifically there. Now, there is another way we could have done that, and that is to just have 3 different bits, one for up-down, one for east-west, and one for north-south, right? We could have done that. And if we did that, then we would just specify one of those and we wouldn't need to know. There's pros and cons to each, but I think this way probably ends up being better because it doesn't introduce another set of ways of talking about the directions. We already know that plenty of our code wants to talk about specific surface indices. So just having this code also use that nomenclature, I think probably will prove to be right, because I think both ways are a little messy. Neither solution is perfect. And so I think that just picking the one that can be used in more places more often is probably the better choice when faced with 2 imperfect solutions. And so unless we find something a little bit further down the road that really makes us go, wait a minute, no, it should be the other way, I think we want to just stay with something that's more explicit. So yeah, I don't know what we want to call this. Like, what are up and down? You know, the problem, one of the real problems is that in the real world we use terms like vertical to mean things that go up and down, but in the game world, when you're looking at a screen, oftentimes horizontal and vertical, neither of them are up and down, right? They're both used to describe lateral motions that are in the plane. So I don't know. Yeah, I don't know. We're going to leave it like that for now, because that's what I can think of. So there's our mask, and here's our indices. Those are all nice and tidy now. And now we have a direction mask from A. And what I'm going to say is that the direction mask from A, and I suppose I can just call this dir mask from A. Don't need to get too verbose there. What I could say there is when we connect two rooms together, and you can kind of see where I'm going with this, 99.9% of the time, the way that we're going to connect rooms, probably, I'm guessing, is to just say, look, it's going to be planar, right? So, and in fact, all of the connections we did so far were all planar connections. We didn't have any other specificity, but they weren't vertical. So I think that that's a reasonable way to do it, because most of the time that's what it's going to be. So all of our code right now is now implicitly saying these have to be planarly laid out, right? So now I think we're good. But can be direction, because of that sort of realization that dir mask kind of has to be relative to something if we want to be using specific directions when we specify it, can be direction is not really sufficient, right? The reason it's not sufficient is because when we're talking about a connection, we don't know whether we're A or B if all we specified was the connection. So what we need to do here is say, all right, we need to talk about can be direction from a particular room. And so when we say, could we go this direction, we need to know which one we're talking about here. Now, can be direction for this particular thing, which one are we talking about, right? And that's crucial here. Are we talking about, how are these rooms getting placed? And so what we're doing is we're placing this room. And so what we want to do is look at how we wrote this code. If we come in here on axis 0, positive, false, essentially, right? So dim 0, side 0. If the side parameter was 1, it came in here. If the side parameter was 0, it came in here. And so that's saying that, well, where we're going to try and place ourselves in the case of a negative axis means our minimum has to be less than the maximum value of the other room, right? Which means we're sort of to the min side of it in the case where we're negative. So that to me suggests that we're talking about this sort of backwards, if you will. Because can be direction is sort of saying, oh, if I've got can be direction is saying, here is the side and axis. I want you to tell me whether I could place the room in that direction, right? So that means that A has to be the room that's given here in a sense. So probably what I just need to do is allow you to ask either one, right? I'm pretty sure of that. And so if we take a look actually at how that works, I'm just going to go back here to box. So what's interesting about this is these are all sort of like complementary. So basically, if you just switch which ones you're talking about, I think at that point you're fine. So I think we can bitwise do this. Let me go ahead and sketch that out for you. So if I want to ask if I can go from A to B, then I just use the mask as it is. If I want to ask whether I can go from B to A, I have to do an inversion of the mask, right? That flips these directions. But that's actually pretty easy to do. I don't know what to call this. Get box mask complement, maybe? So in this case, I need to construct a result. And what I want the result to be is I want it to be east if it was west, or west if it was east. North if it was south, south if it was north, right? I just want to flip those. And what you can see is they're lined up, right? I've got 2 bits for west and east. The next 2 bits are north and south. The next 2 bits are up and down, right? So what I can do is I can mask off half the bits and half the bits, right? By being creative. So I can make a thing called a half bit mask here, which is box mask, oops. And I suppose I could really just do it this way. Right? So I'm just taking 1 in the bottom, 0, 1, 0, 1, right? Which is west, south, and down. And what I can do is mask those out, right? And then mask the other ones out. So just west, south, down, just east, north, up, right? It's basically what we're doing here. Otherwise, I could also say just odds, just evens, right? And I could call this the odd bit mask. You know what I'm saying? I guess if we wanted to say bit 0, bit 1, bit 2, maybe you would call this the even bit mask. It depends whether you want the 1 bit to be called 1 or 0, and then here's what we'll say. How's that? Now there's no nomenclature. So what I want to do is say, all right, let's take the box mask and AND it with the bit mask, and let's take the box mask and AND it with the bit mask shifted up by 1, right? So when I AND it with this bit mask, what I'm going to get is just the 0, 2, and 4 bits, and when I AND it with the bit mask shifted up by 1, I'm going to get just the 1 and the 3 and the 5, right? And all I want to do now is just swap them out. Again, really easy. So all I'm doing is saying, okay, once I've masked out the high bit in each pair, I can shift this up and OR it in and have moved the low bit to the high bit in each pair. The same is true for the opposite. If I have the high bit in each pair, I can shift it down and OR it in, and now I've swapped the high bit with the low bit, right? So this just moves the ones to where, this moves the low bit to where the high bits was and the high bits to where the low was. It's just a swizzle, just a 2-bit swizzle. So that's it, right? Yeah, that's all I wanted to do. So to get the box mask complement, all you have to do is just this bit pattern here. It's very simple, right? So what I can do in terms of going back to my world gen, I can now ask either way, whichever one I want. So I can say genroom from. So I can say can go direction or something like that, or can, or maybe like could go direction from this room over this connection. And then what I can say is, well, we need to compute a dir mask. It could be this one, which is the one that's already in there. But if the connection isn't A, so if it's actually B or something, right? Then I need to do the complement of it to flip it other way around. And that's it. So now I think I can ask that question however I want. And that's good because that way all the rest of the code doesn't have to think about it anymore, which is pretty important, right? I thought I did change it to dir mask from A. Did I not? Oh, dir mask from A. There we go. And so now we can just call what was it? Go direction. Now we can pass whichever room we want here and then pass the other things. So what I want to know, I think I wrote this, like I said, the other way around. So what I was saying is we're placing this room. So I want to know if I could go the direction from the other room. So what I'm actually saying, I think, is this. Can I go from the other room to the room I'm placing in that direction that I'm saying here, right? And so now I can just ask that question the way I wanted to, and I think this falls out. So we'll verify that later. Just to make sure side is correct there. I think it is, but yeah, don't quote me on that. So all that stuff is fine. When we get down here and we're going to do our max allowed dimension, one of the things that this, I think, fails to take into account, and I wish that it would, so far, is this doesn't really handle the first room very well. So when we get to the first room, you can put it anywhere you want, and maybe it's fine to stick it all the way at the very earliest part of the, at negative 2 billion or whatever. Maybe that's fine, but it seems like we maybe want to place it more centrally around 0. You know what I'm saying? So I think in some sense we may want to special case that first room so that it starts out more towards the center. And we actually can do that, I think, without really doing much else. What I could do is just here have something like place room in volume. As just sort of an understanding of what's happening there. And what I could do is say, look, let's just place the first room wherever we're going to place the first room as a seed point. And then we'll go from there. So when we actually, this is not the routine I wanted. So when we actually put the first room on the stack, let's actually place the room in some volume that we want. And let's also set its yeah. Let's do this. Let's not push that room. Let's push the connected rooms instead. And we'll set its generation index, right? And that's just so I can sort of say where I want layout to start. And I realize that that's not maybe actually necessary, but I just want to do it so that I can control where the first one goes for now. We may undo that assumption a little later on, but for now I just want to do it. I don't know what we want this initial room to be quite yet. And again, we're going to kind of play around with that a little bit later on. But for the moment, I just kind of want to do this manually. Yeah, we're going to have some problems with this, but I just want to do it manually for now. So that room goes from -4 to 5, maybe. Well, let's do it -4 to 4. Let's just do that, and that's where the room's going to be for now. And we'll consider that placed, and we'll push its connected rooms on, and that'll be that. So that's all fine. Oops, that's not what I wanted. So that's all fine. And dandy. And I think that should give us the ability to start debugging the code now. So let's go ahead and step in. What I want to do is start debugging at the place where we do the layout. And I'm so weird that oh, you know why? We're compiling in release mode, which I don't want to do. So let's go through here. And let's take a look at our stack. You know what I just thought of too? Before we start, I want to do something even more ridiculous, actually. Now that I think about it, when we talk about the rooms here, when we're debugging, this is going to be a real pain in the butt because we have no idea what we're looking at, right? And so what I might do here is something like this. I'm just going to stick a debug label in there, you know? And then when we do our actual room creation, so, you know, when we're down here in the gen room sort of phase of things, I'm just going to pass what the room was, right? And you know, we can be as descriptive as we want here because these things don't get shipped. Maybe I'll go caps. And this way, because the first thing we're going to do is we're going to see a stack of stuff. I want to see what they are, right? Like what's in that stack. And we're going to have no idea. There's just going to be a bunch of bundles of volumes, and we're going to have no idea what they are. This way, I'll actually be able to see what they are. So then what I can do is go up to the genroom function, and I'll just define the genroom function to actually be a macro. And so that way what I can do is say, well, there's actually going to be 2 versions of this thing. And when you call genroom, either you are going to call the version that has the gen, the spec, and I guess this will be the internal version, the spec and the name and the label, I should say. Or you're going to call the version that doesn't have that. And that way, it'll just get stripped off. So when we're not compiling the internal version, it'll just go away, and that'll be the end of it, right? No big deal. So then all we need to do is, in the case where we did actually have one, let's assign it. Oops. And who knows, maybe we'll decide this isn't a debug label, and eventually we'll just print the name of the room. Like maybe that comes up in the game. And then I'll just get rid of that, and we'll always have that. Could do. Oops. Okay. So now we can be a little bit more introspective here. So the side alley is the thing that's getting placed first. And then if we look at the stack, what we should see is just to, you know, we can predict what we want to see on the stack if the code is working properly. The orphanage specifically says that the side alley, right, is connected to the forest entrance and the backdoor path. So the two things that should have been there are two things that should have been pushed on the stack, those two rooms. Right? Hey, look. We have nothing on our stack, so obviously we have a bug. So first place things first, we can go ahead and go here and take a look at what happened. Right? If we look at the first room here and we look at the connections, you can actually see that there are connections. So it does seem like the bug is just in push connected rooms, right? Oh, well, that's the problem. We're looking at the wrong... So as you can see here, we're pushing the other room, but for some reason testing this one. Well, obviously this one has it set. Duh. Like, we're working on this one right now. So that's a pretty simple bug. Maybe that was the only bug. We'll see in a second. So let's look at the stack top now. Here are the two things that are on the stack: orphanage backdoor path and orphanage forest entrance. That's what we wanted. Well, I had it up here before. Let's get it back. That's what we wanted, right? Backdoor path and forest entrance. That's the two things connected to the side alley. So that's exactly what we want. And let's go ahead and see what happens next. So we grab a room off the stack, and it turns out that the room that we get should be one of those, right? Orphanage backdoor path. So now what we need to do is push all the connected rooms onto the stack that are from that room, right? And so let's go ahead and do that. Again, we can look at the stack and see what's on there. If we look at the top, prev, we've got two rooms. And so what we have here is we have the forest entrance and the orphanage main room as well. That's exactly right. The orphanage forest entrance is connected to both the side alley and the orphanage main room. Again, walking just right. Let's go ahead and grab our min-max vols here. So our minimum volume and our maximum volume start out, they should have the entire universe enclosed in them. And you can see that they do, right? Negative maximum to positive maximum, all well and good. So now we need to figure out whether we can place this room. This should succeed if we have no bugs, because there's only one constraint on where we place this room. So it should work, right? Now it probably won't, because we probably do have a bug. But point being, this one should work. Eventually we'll get to a placement that should fail, because our current code is not good enough to handle loops and stuff like that. And there's all other kinds of bugs it has. It's not checking for overlap, so our current code is not good enough at all to do the right layout. But for this particular part of the layout, it should work. So here we go. We step down into the place room function, and we're talking about connections that this room has to have, right? So we start with the first connection that it has to have. And again, thanks to that handy little debug label, like I said, this becomes a lot easier conceptually for us because we can kind of tell what we're talking about here. If you look at the connections, we can see what's connected to what, or what's supposed to be connected to what, by looking and seeing that we're talking about a connection from the back door to the side alley, right? And we're trying to place the back door path. So we're basically saying, well, let's look at where the side alley is, which I think was the first thing we placed, right? So we can see that that already got placed because it's got a generation index of 1. And so we're talking about these two getting placed now, this one that we're on right now getting placed. So we look at these two, we should see, again, that should be the side alley, and it is. So we're talking about the side alley and, again, the back door path, right? And then we go through, and we're now going to try placing it on one of the sides. So the first thing we do is say, well, if we were going to use the x-axis negative, right? And again, so that's west. You know, if we were going to place it west, could we go west? So let's go in there and see. So we look at what the direction mask from A is. The direction mask from A is 15. That is what we'd expect, right? Because all bottom bits are set. East, west, north, and south all set. So that's going to be everything up to the 16th bit set, or the 16-bit set, right? Not the 16th bit, 5th bit. So all bottom 4 are set, which is 15. That's what we expect. So now we say, look, which one of these are we, right? It turns out that we are actually the B connection, so we need to flip it. So we need to do that complement. So let's see if that code works, right? We've got a bit mask here. You can see that bit mask is set to 21 because it's every other. We mask out the two halves of this, right? So we get the 5 and the 10, split it up, right? And then we flip it around. And as you can see, we get the exact same result. That's what we wanted, because if you have north and south set and east and west set, but not up and down set, then the complement of that should still be north, south, east, west, because, again, you can be any of those, right? So there we go. Now we want to look and see, okay, for this dimension inside, which index is that? Well, that's index 0. Exactly right. Is that allowed in here, right? Oh, we have a bug. Good, we found a bug. That's wrong. This is the surface index, not the surface mask. Now, that was pretty obvious and pretty obviously a bug because this says get surface index, not get surface mask. To avoid that problem in the future, or to make it easier for us to be more likely to do the right thing, let's also make a get surface mask, right? And that way we can call either of those two things, and I feel like that would make it a little easier. Like that. And that's just, again, really straightforward. There's nothing interesting about it. All we're going to do is say that we take whatever the surface index is and make a mask out of it. Right? Okay. Let's jump right back in there. As the first time we ever called that function. So let's jump right back in there and make sure we do it right. Test mask is 1 now. That's what it should have been, not 0. Result is 1, which is true. We can go that direction, so that's good. So then what we're going to do is say, all right, let's make a new volume here, and let's clip it. So this is where we're going to place the new room. We tested whether we could go in the negative direction from other room. This means we need this to be placed to the west, right? So let's take a look. We've got new min vol, new max vol. This is where the minimum can be placed. So let's go ahead and see where that clips to. And this basically says that the maximum for our volume can be placed at 4. The minimum for our volume can be placed no further than 4. Now, I feel like we got the sense backwards. So the thing that I was afraid of, I think is true. Right? That's not correct. These should be the other way around. The reason I say that is because this should be placed to the west. This placed it to the east. You know what I'm saying? So we've got the sense of that flipped. So if we come in here and we're placing it in the positive direction, we're setting the max to clip downward. So, and that's wrong. So this should be the other way. Is what was messed up about that. Right? Oops. And perhaps if we wanted to be more specific about it, we could also use the minimum room dimension in that direction. So this is our max. We also have a min. We could actually pre-constrain it. Well, I'll just leave it like this for now, but we may want to just pre-constrain that part as well. All right, let's keep going. All right, so we could go direction. Now we're going to clip it, and we should clip it properly this time, I believe. And here you can see, yeah, this is right. So now we're saying the maximum, right, both the minimum and the maximum could have been would be at -4 now. Right? It can't go any further than that, if that makes sense. So I think that's what should have happened. Let's keep going. So if I look at how it's clipping the other dims, here's the y-axis. So now what we should see is it has to be overlapping that room somehow, right? So what we should see now is the y's should be set up so that between -4 and 4, you're going to get those for your other dimensions, right? So the y max can't go any higher than 3 for the minimum of the room, and that's correct, because if it went any further, you wouldn't be able to make a door. And for the maximum volume, you can't go any lower than -3 because then you wouldn't include -4, so you couldn't make a door. I think that's right. So that all seems sane. What I will say is I think that I probably want the starting room to just be 1 high, though. Oops. Didn't quite want to get there yet. I was trying to step through this code. Okay. So after we've done one clip and we've got it in here, right? Then what we want to do is get the maximum volume we could fit in here. And so what that's going to be is massive, right? It's something that could be really large, really huge, right? If we wanted it to be. And okay. Okay, so is minimum dimensions for a room. Ah. So this is a case where we're going to have overflow, right? Our problem here is that this subtraction is going to produce a signed result, which is bad for us. Because we need to have another way to do this. So what we want to see is if these are greater than 4 away from each other. And the problem that we're having here is when you subtract the max from the min, that number may be higher than is representable in an S32, right? So there's a couple ways we can do that. One way is just restricting the range to be smaller than that. So what we could do, the trivial way of avoiding the overflow is to just say that our infinity volume isn't such an infinity after all, right? And then we would be fine, I think, if that makes sense. So when we now go through is minimum dimensions, we should be able to make it work, although the fact that it's not, maybe that code is just buggy in some other way. Let me actually also do this. So if I compute these dimensions first, then we can inspect them pretty easily. And I should be able to see what's what. So that is actually backwards. So, okay. So no overflow problem there. That is actually just busted. So that's okay. Let's go ahead and see what's up with that. So if we look at our min volume, yeah, our max x can only go up to -4 for some reason. So it looks like maybe we've got a bug in that clipping routine. Yeah, let's take a look at that. So here's my new min volume. That was not causing the problem yet. Here's my new max volume. This was causing the problem, right? So what I'm saying here is if the maximum value that the maximum could have taken was greater than the minimum that this room is, then I need to back it up to there, right? So I guess I see what the problem is. The problem is that the minimum volume, well, no, I guess I don't see what the problem is there. So that's still right. So what, I'm just getting confused because there are so many values here. I try to think all through. That's still correct. You can't, the maximum value can't go higher than that. And the same would be true of the min, right? They're both going to be clipped there. So that seems fine. So when I get down here, yeah, having the minimum volume's maximum is -4, and it's minimum. So that's the actual value that's wrong. Is the mins are now non-negative. Right? So that's the problem, is that divide is too sloppy. Right? So the minimum value divided by 4 is not able to actually do the divide by 4. Is it actually because of that? I don't want to say why because I'm not sure why. So let me just make sure. This is just C doing its thing. Yeah, so what was happening there, and maybe so what we should do, I guess, to maybe prevent that from happening in the future, is just when we define those, maybe we have to force them to be the values that they are, the types that they are, because what it was doing is it was converting that value to an unsigned integer and dividing it instead of leaving it signed. Through C's magic fun integral promotion rules, I'm sure. So now that should be correct, right? And do we still have a breakpoint set there, I hope? Let's see. Yes, we do. So now when we do is minimum dimensions, it should work, and it did. So now we can go in here and call place room on the next connection. I don't know if there was a next connection. Was there? There was, but it doesn't have the generation set, so we don't have to consider it. Oh, but we don't keep chaining. So we're going to need one more thing here, right? We're going to need a thing which continues to chain the room. So here, when we went through and we said if roomcon else, right? But what we actually need to also do is we need to continue placing the room in the case where the generation index doesn't happen, right? So if we're skipping this connection, we need to keep going. So now that I think about it, probably this is just a dumb way to do this. We could just speed this up a bit by just assuming that that's always the case, and spinning on the roomcon afterward, right? Something like this. So basically say, look, let's just walk this thing until we find one. You know what I'm saying? So we'll come in, if we have a room con, we'll grab out what the other room is from that connection. If the generation index matches ours, then we can process it. Otherwise, we keep going, right? I think that's all we need to do. Okay. So, this is correct because the first room connection is one we can actually process. So we go through, we do our clipping. As we wanted to, and then we continue down recursively. In this case, we know that this other room hasn't been placed yet, so we skip it, and then the room con is null. So then we can come down here and actually place our room, which is what we want. So we have a min and a max here that we create. We know that they're going to be very oddly placed rooms here. Yeah, because that first one it should violate where we placed it. Although this still seems wrong. You take a look at minvol maxvol. So here's the minvol. And the minvol says it can be anywhere from here to here, right? Here's the maximum volume. And that's just, that doesn't make any sense. Does it? Yeah. So there's one additional element to the clipping here. Yeah. When we say that this thing has to abut the other room, we're not saying that the maximum can be anything less than it. We're saying that the maximum has to be exactly that, right? So effectively what we're saying here, that is just nonsense what we just said right there, right? That was not correct. What we're actually saying is, okay, if you're connecting on the positive side, right, then the minimum must line up with this, right? So we have to be able to move the minimum here, right? Otherwise, it wouldn't be able to connect. Now, this means we could fail. And that's one thing that we weren't really accepting here. But yeah. So basically what we need to do here is say, all right, the maximum can still do whatever it wants. It can be as far out as it wants, but it would have to be at least this far. So that's still fine. The minimum volume, on the other hand, has to be exactly here. And if I can't move it exactly here, then we have a problem, right? So if no, so I think this is fine. So that's all we have to say. So if the minimum could not have been placed exactly here, then we have an issue. So we need to basically say if the minimum value is greater than the place that we needed to put it, right? If it already can't be there, then we have a bug. Otherwise, the minimum has to be there. Does that make sense? We're basically saying this thing has to be placed literally exactly here. There's nowhere else it can go. And I think that's what we actually want. And so if for some reason you weren't able to do that, so if the minimum value that we would have accepted before for where it was going to go doesn't allow us to actually get here in the first place, it's already further that way, then we're toast. And I guess we don't really have to do anything about that now that I think about it. We can just do like new minvol, you know, or something like this. So we can just say like clear it out, like it's over at that point, right? The same would be true on the other end. So when we needed to connect the other way around, we need to do the same thing. So we need to say something like, well, okay, if I'm going to compare the mins here, I just need to make sure that the min can't be any worse than this. But the same thing that happened to the min up here has to happen to the max, which is to say that I actually need to be able to set it to be exactly this value. So whatever the minimum value was on the other room, that has to be the maximum value on this room now. It can't be anything other than that. So I think that's right. And then again, if for some reason we can't do that, we have to invalidate this volume, and so it won't actually work later when it does anything. The new max, the test here is going to be similar to the test here, which is to say that if the maximum value was already lower than this, right? Meaning it could not have been placed here, then we're done. There's nothing we can do about it, right? Because we can't move it out to here at that point. Right? So I think that's right. And then we just need a way to basically make one of these and I think I can just do that. Let's do it this way. Okay. All right, so now we should be able to step back through that and have it work more like what I wanted it to do, as opposed to what I wrote before, which was not what I wanted to do. Let's just take a quick gander here. what we actually end up with now that we're here. So if we take a look at the minimum placement, here's the minimum for everything. We take a look at the max placement, and you can see the difference now. The max has to be basically exactly here, right? It can't be placed anywhere else. So let's see what we get for each of these dimensions. And that looks about right. Again, we're not doing anything special here to try and keep ourselves from creating large rooms. It's just going to create the largest room it can in the space, which is not good. I mean, it's not what we want. Although it looks like it still wasn't quite able to place it. Let's try that one more time. I want to see when that happened. Because the result is true, so this must be this one. No? So the min is 0, and the min volume max is 0. So I think we just have an off by 1 error in that clip on the interior then. It's actually probably just because of how we're dealing with Z. Because the max Z should be 1. And in fact, the min Z and max Z should have to be 1 there in order for them to line up, right? So those look actually a little bit backwards to me. Take a look at that. So that's this code here. So so you can see it's setting the maximum, right? And it's saying if the maximum value is greater than whatever the apron value is there, right? Then it has to be equal to. So I would have thought that this would have taken care of it. If the max was less than or equal to the minimum of it, it has to be 1 over that. I'm going to step in here and see what these come out to be. Yeah, but that looks like the only thing that's misbehaving. So I'm going to go ahead and get in there. I'm going to skip the Y for now. I'm just going to look at the Z value. So here we're now on Z. And when I come through here, I want to look at what is going to happen to these values. So you can see we've got the min Z and max Z that these could be are totally wide open, right? There's been no actual clipping of them whatsoever. And, you know, I'll be honest, I don't know why this part hasn't happened yet. Oh, whoops, because I'm looking at the wrong ones. So the z values are not not been changed at all, as you can see. Now, how the x values and the y values both got changed? Oh, because we were already on that. We've already looped through that, so that's all good. I think that's what we would expect. So we've got min z's and max z's that are full range on both right now. So as we step through here and we do our clipping, what we first want to do is say, all right, we're talking about where the minimum point can be placed. And we say if the maximum here is greater than whatever the maximum of the other room is, then we would no longer overlap. So we need to make sure that it's far enough back, right? So that sets the maximum point that the minimum z can be at 0. That's correct because really, well, no, it's not. So I suppose since in this case we're talking about these things as not being inclusive of their maximum, it actually still needs to be +1. Right? Because that's not the maximum value that the max could be. It's one more than the maximum value that the max could be. I hate crap like this. Discrete math is the worst. Unfortunately, it's the only thing computers can do. Anyway, so when we actually do that clipping, right, if we want to be consistent here, then the maximums always have to be one more than what they would otherwise be. So this is actually still this. Because the max has to be placed at wherever that location would be, but +1 to include the room. And then, like, I'm going to put the two minvol updates sort of back to back here. So, right, to set the minimum value for where the minimum can be, we do move it back. And that's, yeah, so this is going to have to be true in the other case as well. So to set the minimum value here, we need the min plus the interior apron Yeah, so we've got both problems here as well. So what we need to do a couple things. First of all, we need to make this line up right gap-wise. But the other thing we need to do is we need to do the same thing we were doing here, which is to say, when we actually find one of these that has to be updated, we have to also make sure that the update is legal, right? But I guess since we're only checking for the greater thans, that's already going to happen. But we need to, like, this needs to include failure as well, I guess is what I'm saying. So in both of these cases, we kind of want to be able to set an inverted infinity volume in the case where we find that we've failed, right? We don't ever want to set something in a way that makes something legal again that was illegal previously. Because we always need to make sure that there's no way to undo a person's constraint. So when the boxes are only ever allowed to get smaller, right? We're never allowed to like push something out that would make something bigger than it could have otherwise been. So I guess anytime you see this, where you're taking a minimum and you're pushing it out, it's fine. But I have to make sure that we're never doing anything worse than that, right? So basically, like, this needs to always look, I guess, like this. So you know, it's okay. Because we're always saying, look, if the minimum was greater, we're pushing it back, that's probably okay. But if the maximum was already on the other side of it, we need to kind of fail. So I suppose, right, I mean, this is all I'm trying to say here. Like, we need to fail out here if we don't overlap. I guess if that makes sense. Like, we need to say, oh, if the min is greater than that, then put it here. But if the max, something like this. If the max already says we can't do this, then we're also fail, right? Meaning if the max was, let's say, set up such that the min can't possibly end up in this range, then that's a fail. That's the part that we weren't doing before, right? So in addition to this part, we also need to nuke it in the other case. So if the maximum place that we would have put the minimum value before, right, can't reach, if it's less than the place that we needed it to be, I guess we can call that the min. So if the minimum value before, this is mind-bending. I hate writing code this way. This is where you just want the diagram, right? Because the diagram is perfectly clear. But then when you actually have to write the code, the names are so obtuse and there's so many of them that you are always getting some permutation wrong, right? Where you're thinking like, okay, wait, this is a test for greater than the minimum's minimum value, you know? And it's like, that's just a horrible way to describe this. Because not only do you make a ton of mistakes when you write it, but anyone who has to read it will never be able to like map it properly. Whereas if it was just a diagram, you'd be done, right? It'd just be like, oh, that's the things. This has to go there. That has to go here, right? It's like trivial when you draw it. I'm not even bothering drawing it because we all know what it would look like when it was drawn, but it's trying to like type in those things that becomes incredibly difficult, and you end up like having to alt-tab back and forth to your diagram all the time and still getting it wrong, right? So it's just, yeah, it's maddening. Anyway, so this is the location at the far end of the room, and we're saying that the minimum could be, it's got to be less than this. And so so this is just illegal. This is just wrong. I don't think these tests are set up right. I think they're backwards. So here's what we want to say, right? We want to say, excuse me, that if the minimum value was passed there already, then this is just illegal. Right? Because if you're saying that the minimum value couldn't, so if this minimum value was greater than or equal to what we're talking about here. So the max, it's got to be back 1 from that and then back 1 again, right? Yeah. If the minimum was already greater than or equal to, so if it was greater than that value, then you can't place this thing. Because you're basically, our constraints say it can't go there, right? Otherwise, we do know now that the minimum has to still overlap the other bound of it, right? And that's really all we can say about the minimum. So I think this actually looks more like this. So the other room's volume, it has a minimum and a maximum. And so we know that our minimum and our minimum value, the minimum value then has to fall within a particular range. And that range can be anywhere prior to the max, which is this guy. And I suppose we don't need this guy yet, but we will in a second. So if the minimum goes over that value, then it's illegal. If it doesn't go over that value, well, I mean, that's really it. That's the only thing we're checking that value for, right? Yeah. So basically, we know that the minimum value there has to be greater than whatever this is. I'm sorry, can't be greater than whatever this is. If it was, we would not be able to overlap the room, and we're done, right? The next thing we want to check is the minimum volume's maximum, which is this. And so the minimum in this case, let me just grab this. Well, that is exactly what we're talking about here. So, well, no, it's not exactly. So the min here, this is where that is. The maximum value the min can be has to be greater than this now. This is just wrong. I don't know why we wrote this. I think that was part of the bug. Right? So the minimum value is just whatever the interior apron is here. So whatever the maximum value our minimum can take, meaning the furthest we are allowed to slide our minimum, right? Wait, no, that's right. The furthest that we're allowed to slide the minimum now has to be here. Here's a question. Can we just do this in a simpler way? Because look at how much time getting spent on there. And I think it's mostly because I'm hand coding the intervals effectively. If we just did the interval properly, I wonder if this would just work. So if we think about what has to happen here, so what are we saying? In the case where we know we have to clip it to one side of this volume, right? We're saying that this, right, the maximum value here, we're saying that this thing has to be we're saying that this thing has to be starting there and it can end anywhere on the other side of it, right? That's why we have to do this inverted infinity volume stuff here, is to peg the value to a specific location. In this case, now I'm starting to think maybe it's okay the way we were doing it before, because since we're always updating the values, they should just cross in the case where they can't have happened. So we shouldn't actually have to check it, right? So let me just see if that's the case here. Okay. So in this case, since we're talking about, and let's just again move these so that they're in the same place here. So if we're looking at these and talking about always sliding them, if we always slide them the other direction, we should be okay, I think. Because in this case, we're only ever clipping to, we're not having to peg. We're just talking about the range. So we should be okay with that, right? And if we wanted to here, I suppose we could even do this the other way around. I mean, you just need both checks. The problem was we were only doing one of the checks, right? But in theory, you could actually do that. So you could say like this: if the new min-vol right? So if the minimum was less than this, it becomes this, right? So we're moving it forwards. If the new min-vol max is greater than other room vol right? So I think that's more like it, right? The way that I should have been writing this was you always just adjust the bounds towards the direction. They're only allowed to move one direction. And then the bounds just cross each other when you get an invalid volume, right? So I think that's it. Again, so writing this other one the same way. Then we're just saying, okay, if the max is greater, then the max slides back. If the min is less, then the min moves forward. Right? And so probably what we should do is just make these be an actual routine we can call that would clarify this a little bit better and make it so that it was less verbose, right? Where you're updating one of these things. And you can imagine what that would look like, right? So this would be what that would look like, meaning clip the minimum to this, and that slides it forward if it's less, right? Here's a way to clip the max. Right? And so that seems probably like what I want. And that way we can just say like, okay, there's the function here. It looks like this. It has a volume. It takes a dimension, and it takes a value. And then it just looks like this. So now we've got a clip min and a clip max. They operate inversely, comparison-wise, right? And what we could furthermore do, I don't know if we really want to do this or not, but what we could do is incorporate the max version into this. So basically saying that like if the max is supposed to clip to this value, it actually clips to the next value. Because we know that max is supposed to be inclusive. This way, if you clip the min and the max to a value, it would move one over, right? I don't think I want to do it that way. But you could understand why someone might, right? So there's that. Oops. So here we have clipping the min and the max to that value. That just looks a lot more straightforward now. You can see now how these are sort of split out. So in one case, you clip the min and the max of the min, and you just clip the min of the max, and the other ones you clip the max of the min and the min and the max of the other two. So one of them always gets pegged, and the other one doesn't. Right. So again, it's still really hard to read. Like I say, you really want this to look like a diagram because it's just, you know, I mean, now it's a lot more condensed and it's easier to see what's happening, but it's still really confusing. And the reason is because you have mins and maxes of mins and maxes. You're computing intervals of intervals, right? And that's just very easy to see in a diagram and very hard to see in code because you just got all these names flying around. That's the only way to really refer to anything. So then when we come in here, though, now we should be able to simplify this a little bit more and think about what needs to happen here. So we've got two things operating on the min vol, two things operating on the max vol. So what we want to do is we want to, in both cases, clip the min and the max of both things. The question is just what do we want to clip them to? Right? So what we want to see here is that the lowest value the low can go, right? Should still be anything, probably. Am I wrong about that? It's really just that the maximum can't push past. Oh, and the minimum can't push past. So the minimum value, it just can't be past the location that we want to be before. So the maximum minimum, so we only have to set the maximum minimum value and say that the maximum minimum value, or I should say the minimum, well, no. The minimum value and the maximum value of the minimum should in theory be able to be anywhere you want. But the maximum value of So yeah, okay. So now I'm starting to see why this is confusing. So really, it doesn't really matter where the minimum maximum values are. It just matters that they overlap. So if the maximum value, you just care where the maximum value of this thing is, has to lie somewhere within this if the minimum doesn't. And that's not representable by an interval, right? So I think actually the nasty part about this, that first part's nice and clean now, but the nasty part about this is actually that we can't really propagate this information forwards. Can we? So the fundamental problem that I'm talking about is we know that we need to overlap this or the two rooms won't touch, right? So, this is a room that's already been placed. If we need to overlap this, the definition of overlapping is just if the minimum lies within it or to this direction, then it's in, right? Well, the minimum value has to be such that its maximum never passes this, right? And the maximum has to be such that its minimum never passes this. And that we can represent. But once you have that satisfied, you still don't know if you actually overlap. Because let's say this is the region that you actually end up with, right? Here are the plausible values for the minimum, and here are the plausible values for the maximum or something, right? It'll always overlap. If you instead say, well, here's the plausible values for the minimum, and or let's say, here are the plausible values for the minimum, and here are the plausible values for the maximum. Yeah, I mean, I guess what I can say is we can always ensure that you would include this, but you'd have to ensure that you include all of it, is the problem. Meaning a room that just looked like that would never be allowed. Right? Because if you allow the if you allow, I should say a room that looks like that would never be allowed. And the reason is because if you allow the minimum to be down here, once it can go fairly far this way, then you no longer know if the maximum, say, could be anywhere in this range, or something like that, then you no longer know, do you, whether you could place that room. Yeah, I don't know. So let's think this through. Let's actually just try it, because I find this very confusing, and I think I just need to work it through a little bit more carefully. So in terms of the minimum, it doesn't matter where it is, right? Because as long as the room was long enough, right, you could put it as far minimum as you wanted, right? So really, the minimums, it's just the maximum is the only thing that's clipped. And the maximum has to be the maximum has to be such that, excuse me, when you're moving the minimum, you cannot move it past the room. So in this situation, like that, that's as far as it can go, and it can't go any further than that. The maximum, on the other hand, is the other way round. The maximum value, it can be as high as it wants, right? So we don't care how far it goes the other way. But when we're actually moving it back, we can't move it back past where it would still overlap the room, right? I think that's right. So that location would be at the minimum plus the interior apron plus 1. Right? So those two things are true, right? Now, now the question is, what about the other bounds? Because we're talking about the region in which the maximum could lie. And so when we're talking about the region in which the maximum could lie, we know that the minimum value for the maximum cannot go past there, but the maximum value for the maximum could be as far away as we want, right? I just don't think there's any limitation on that unless I'm thinking about the problem wrong, because that box that includes it can be arbitrarily large, I think, and the same is true of the minimum, right? It can be arbitrarily small in the other direction. So I think that's about right. That's what I'm going to say. So let me just see where we're at with that in terms of the rectangle we now come up with. Okay. So let's see here. Yeah, looking at this again seems still slightly off because so I think that's the interior apron problem again, which is to say that the interior apron actually needs to be 0 on Z because we don't have the same requirements on Z. So I guess we would say that. So let me just try that one more time there. Right, because we don't want to like do the interior apron on Z's. So the min-max Z's are now set roughly correctly, I think, because the min-Z, it will overlap if it's anywhere negative, or anywhere to infinity, but it can't go any higher than 0, right? Because it's got to line up there. And the same is true in the other direction, right? The rest of the values here, I guess, I think that's all sane. Min x, min y. Yeah, so that looks relatively sane. Let's see what room we come up with here. The minimum value for the z is 0. The minimum value is maximum value for the dimension 2 is... Wait, that's not true. Oh, it is true. So that's actually, again, that's to be inclusive, that has to actually be 1. So how did we not get that? So when we're clipping in here to the maximum value and the minimum values that z can be, just trying to think it through here. We know that we know what these values are. So the minimum value in case of the other dimension is 0, right? So then we're going to add the interior apron, which is also 0, and then we're going to add 1. So it seems like that should just produce 1. Shouldn't it have? Oh, and the min volume, of course, is getting clipped to the interior apron minus 1. Which in this case, I guess, yeah, is not what we would... Well, okay. But looking at this... So when we clip the maximum of the minimum, moving it to whatever the max was, we know we go back the interior apron, and the reason we're subtracting 1 there is because we're setting the max, and the max we know is 1 past where we want to be. So we have to go back 1 more further from that, right? But this is clipping the maximum value itself, which already has that 1 built in. That's a mind bender. So it really does end up being that. Then when you clip the max volumes minimum, you're looking at a minimum and you're clipping a minimum, so you don't need the plus 1. I don't think. Because you're starting with a minimum and you're saying you need to be there, right? But I suppose you kind of have the other thing, which is that you also are talking about 2 mins. Man, this is nasty. So when you actually are talking about clipping these two, you've got a max value that is having these values work uniformly might be the better way to go here. Just looking at how many crazy things you have to keep in your head. So it is the max value, but it's also the min volume that you're clipping. So it's where the minimum is going to be placed. So if you assume that you placed the minimum, you need to allow the room for the minimum to be placed there. So I guess that's okay. The minimum value has to be between there and when it's the max of it, which takes it. So I think that's okay. This is just mind-bending. There's too many flip-flops there, in my opinion. So I think we're going to need to look for an easier way to talk about these. I think it's just way too mind-bending to think about that way. So maybe they need to be uniform values is really the only way to look at it. I don't know if that'll introduce other problems there as well. But we'll see. So that's right. That's right. Well, no, it's not. So technically that would not be overlapping, right? So I do think it's asymmetric. In that sense. Let me just double check that. Yeah, so I think that's correct because it has to be that. If it was 0, that would no longer overlap the other room. But hey, we placed that room now, and I think we place it in the right location. This will eventually get to a room it can't place, like so. And I'm interested to now see what we end up with our kind of ridiculous rooms here. So I guess one thing I neglected to think about is we also have to figure out where we want to place our saucy gentleman there. What I'd like to do now is simplify this down to just making 2 rooms that are connected to each other. So if I got rid of all of this, and maybe actually I want to do this. I'm not sure where we place the camera currently. So let's do this. Well, actually I can still leave it there. So this will just create 2 rooms that are connected to each other, the main room and the hero's bedroom. Right. So now we should only place 2 rooms total. And we can actually step through those and make sure they actually are. Right. So we got the main room, the hero's bedroom. Those 2 are connected. We've created those 2 rooms. And that's all we have to do. So now we can go ahead and see what actually happens there. So when we come down here and figure out how we're going to place this room, the first room is already placed, and we don't know which one that is. Let's see. So that's the hero's bedroom. So that's already placed. So then we have to just place whatever this other room is, and this should be the only other room, right? There shouldn't be anything else on the stack, and there's not. And now we can go ahead and actually start placing them. So we come through here and we place them. There is no other connection to deal with than this one. So we go ahead and clip it, and we verify that it actually is a valid volume. So we come through here. Now we try to place the room. See what the room actually says. Seems pretty reasonable. It has to be between there and there. That all seems pretty good. So we take a look at the min and the max. We know roughly where those have to be, so let's go ahead and compute those. So then we end up with a min of -53 and a max of -5. That makes sense. For the next dimension, we can place it anywhere. and then we get down to z, negative to positive. So that got placed. So the room is now placed. And we're good. So I think that's all fine. The only problem that we have here is, for reasons unknown to me, probably just because there was so much stuff for us to think about there, I just never finished the exit path of this, right? So what we want to do here is say, well, look, if you place the room at some point, then you're done, right? So we want all of these to sort of be predicated on the result, and we want to stop looping, right? So if at this point we could even return from inside there if we want to, but I'll just make it so these loops are predicated on it. So as soon as you get one of those, you're done, right? You stop looking when you find one of these results, and off you go. We could also turn this into one loop. And we'll see. All right. So now we ostensibly are placing two rooms, and you can see that we actually did place two rooms there. Here's the first room. So, right, because we know because of its dimension. And then here's the second room that got placed. Now, it doesn't quite look like we did it right because they don't quite overlap, right? You can see that there's a gap here, so we can see that we're off by one. But otherwise, it's correct. It's not probably great, like it's not what we want, but it's okay. And we also need to record the actual connection between those rooms, which is to say we need to place the connection at the location where the rooms actually overlap. So as we unwind out of that, we need to actually do that, right? And I think that's something we probably need to do right here. So if the room got placed, then we know that the connection that we're looking at here needs to actually be put in the place where the two rooms overlap. Because that's where you can walk, right? So that's fine as well, but like I said, we still have a problem with the abutment. So the abutment is going to be coming from here, I believe, because if you looked at how it was erroneously placed, it was this one that was wrong. So I suspect that the problem there is just that, like, well, we're placing the minimum here, and we're saying that the minimum has to be exactly starting at the maximum. And then here we're placing the maximum, we're saying this has to be starting at the minimum back one. But, okay, so it looks like this case is wrong to me. You want the maximum value to actually be literally this value. So I think that's what you're actually looking for. Yeah, and that's correct now. So now you can see these two rooms join up, and they join up in the minimal way possible, right? Probably now we want to push this in the way that I said we wanted to push it in, so maybe you want something more like that. And now when the rooms adjoin, they should have to adjoin in a way that affords more space. You can see that. And finally, you know, let's say we maybe reduce this at the moment to more sensibly sized rooms. So now we've got that. Why am I not? There we go. So now we've got that. And so now we should, in theory, also be able to extend the number of them that we do. Oops. I don't know if this will actually work. Probably won't. But actually, you know, we know it won't work because we don't do overlap testing. So this will like place rooms on top of each other, right? Or something crazy like that. So actually, we probably don't want to do that just yet because we know that won't work. What we want to do instead is probably do something like the forest path so that we've got something that comes then out of the main room. You know what, never mind. I'm just not even going to bother because we need to first do overlap testing before any of that makes sense. Because there's no reason why it couldn't just stick it right on top of the existing room. That would just be totally legal, right? Yeah, and that'd be totally fine. So what we really need to do now to finish up, and then I'll end the stream, is we need to place the connection, and we need to place it in the region where the two rooms are actually abutting, somewhere in there. And so if we knew that door sizes are like 2 wide or something like that, or 1 wide even, then all we need to do is we need to look at which direction we were trying to go and what the actual clip region now is for the two rooms. So we know we have other room vol and room vol, right? And what we want to do is we want to intersect these two. In a sense, right? Like that's sort of what we want to do. But the two are sort of distinct. They're not actually overlapping, they're just abutting. So what we need to do is we need to just talk about the one intersecting the one dimension that we're actually trying to use, right? And we know that they'll be separated by the dimension of the connection, right? So we know that the dimension that we picked here, we know that they are distinct in that dimension, but they should be overlapping in the other ones. So when we get this door volume here, we know that it doesn't have any actual volume, but it does tell us the overlap, right? So the first thing we need to do to fix that is we know that the door in the dimension in question, right? I think we can do it that way, can't we? There we go. So in the dimension in question, we now know that the door should actually sort of take one into either side. So it should cut one into the room on the min side and one into room on the max side, right? So what we want to do here is say, well, we know which side we were doing. So if we were talking about going in the positive direction, so this thing is to the east, if you will, then we know that the minimum value of the door is going to basically be the maximum value of the source door, of the source room, right? And furthermore, we know that's actually one pass where we want to be, so we want to back it up one, right? And then the minimum value of that, we want to back that up one. Oops. When I say we wanted to back that up one, I actually mean we wanted to push it one forward, right? So I believe what we want to say there, right, is that the minimum for this store... No, that was right. Never mind. Yeah, so that's correct. So the other room, we've got its minimum, we're pushing it one forwards. And I guess now that I think about it, we don't even really need to look at the other one at all. Right? It's just that. So we're just going on either side of it. On the other hand, we would want to do the opposite thing. Or, I mean, I guess you could look at it this way. So we could actually say maybe this. Does that make sense? So basically, we know that one of the rooms is minimum will be where it is, but we just don't know which one, right? So we just have to figure out which one it is, and then at that point, we can just set this directly. So now we have placed it there. The question is, what do we want to do about the rest of the overlap region, right? When we intersect these two things, which sort of says what they are. Now, what I'll probably say is, let's just leave that as an intersection for now, and we'll let the whole space between them be intersected there. Let's just do that temporarily. I'm gonna write the intersection routine. So if we have to intersect two volumes, basically what we want to do here is just start with one of them. And then we just need to check each of the dimensions. So what we want to do now is say, well, okay, we know we've got each of these things as a span, and we want to sort of move each one up to the other one's mins and maxes, right? So what we want to do is say, if the, I guess I can even do it this way, right? I can just say, my results minimum for this dimension is going to be whichever one is less, right? So if A's minimum is less than B's minimum, and I mean, we can just say, you know, we just want the minimum. I don't know if we have an S32 minimum, though, is the only problem. Do we? Maybe we don't. Looks like we do. All right, so all we need to do is do this for the minimum and the maximum. Right? Now this would be a union because we'd be taking the minimum minimum and the maximum maximum, and that's not actually the intersection. The extra intersection is the opposite of that. But I'll go ahead and make that as well since I already typed it in, right? So for the intersection, I actually want whichever one is higher, right? I want to squish these two. So I'm taking the lowest maximum and the highest minimum. If that makes sense. And we'll step through that in a second. So the other thing I just realized is we never actually recorded this value. So we need to actually take the connection now. So when we're looking at this particular connection, we need to set the connection's volume equal to this door. Sorry if I'm behind my head there. Um, all right. So now that should be right, although it looks like we've got that backwards. You can see it's clipping out there, which is wrong. So we're close. All right, so let me move to the other side here. So I thought I had this right. If the side is positive, then it's the other room's minimum that we're at, because we're going this way, right? Otherwise, it's ours, because we're going the other way. Right? Oh, no, that is backwards. Yep, okay. That is backwards, because we're going positive, then it's our minimum, since it was going that. Yeah, all right. Yep. So this stuff is just begs to be flipped all the time, accidentally. So there you can see the door being placed, right? And you can see where the door actually got put in. And that's all well and good. And we can go between the rooms as well. And of course, our lighting being slow as it is, unfortunately means if we're in debug mode, the lighting just takes up way too much time to run at speed. But I can compile in release mode, and then we can hop around properly, right? Once we're set with that, we now have the ability to sort of correctly solve for the daisy chaining of these rooms together. And what we probably want to do is narrow the door down, right? Because we don't want the door to take the whole overlapped space. We want it to just be a narrow passageway that you go between, right? So we can work on that a little bit later. For now, we can just throw something in if we want, which is to say that the dimension of the door in whatever the other dimension is, well, I won't even bother, because that's just going to take a bunch more time. So we can go ahead and Q&A now. I would say the big thing that I want to think about going forwards is I don't like how finicky... I don't like the max and minimums being treated differently like that. It just... The inclusive-exclusive rule is just a little too mind-bending. And I feel like it's just going to be annoying. And we're going to... maybe once you have the basics worked out, it's fine. But yeah. It would be nice to deal with those a little bit more succinctly. Would nomenclature like low, high, width be helpful? You mean so that you would have min and max and low and high, so you could remember which one you were talking about, maybe, or something? Would using a range of low values and a range of high values for dimensions be easier than having two volumes? I'm not sure what you mean, Neil. Can you be more specific there? Why are you appending X to those types? That's just if I'm making a notation that it doesn't matter if they're 32 bits, just they have to be at least 32 bits, right? So if I say something is a U32, I mean it has to be exactly 32 bits. If I say something's a U32X, I just mean, well, anything 32 bits or above is fine. And technically, I could be more precise about that sometimes too. I could say, like, actually, this only needs to be 16 bits. So it's a U16X or something like that. And sometimes I go through and actually do that in the code. Sometimes. Did you want to avoid recursion? In the crawler, I did. I didn't want this thing to recurse, and the reason I didn't want it to recurse is because it's going to have to do. First of all, it'll be deep sometimes potentially, and the other because of it'll just if you have long change with lots of branching, you'll end up with very large stacks, and I just kind of wanted to not worry about that. But the other reason is rip up and replace is going to have to go in here somewhere. And I feel like it's probably going to end up going in here. And so I don't really want recursion sitting in there because it's going to be kind of nasty. This thing is just to get us started. So it may want to become non-recursive as well. But at the moment, I don't care. Although now that I think about it, it doesn't really need to be recursive for any particular reason. So it could easily just use a stack as well. Pretty simple stack. But again, I don't know. We're going to have to see how we want to start doing the harder parts of this first. Could the hero walk outside the rooms in this setup? No. So the way that we do movement is very specific right now. You can only stand on a legal square. So, if you tried to walk outside anywhere, you just wouldn't be able to. Even though this is just kind of preliminary stuff here, I suppose, it still forces you to only do the right things. Like, you can't ever stand on something that wasn't marked standable, which I think is generally better, because it means even when we're just in the simple phases of laying out some rooms here, and just have a little debug hero hopping around, you still can't break the game in that way, which is nice. As opposed to, PlayerUnknown Battlegrounds, where a year after supposedly shipping the game, people fall through the world all the time, right? Neil said, low can be between -30 and 5, and high can be between -40 and 20, as opposed to a min volume of -4 and 5, and a max volume of -30 and 20. Neil, I think that is what we're doing, though. Unless I'm misunderstanding you. We are doing, the min volume is the min and max of the minimum. So it's what the low value can be. And the max volume is the high volume. It's but where the high value can fall. So isn't that what you were saying? Or is maybe that not what you're saying? So okay, do you think that languages that interact with the GPU directly, like NVIDIA's CUDA or AMD HIP, would be useful for game programming? Yeah, I mean, there's some reasons why it's hard to use things like CUDA potentially in game programming, and sometimes that's just because they haven't optimized it for being like frame coherent, so we can say like we got to get this frame out on time sort of stuff, because scientific computing stuff doesn't care if they're hitting a frame budget. They just want to compute as fast as possible and so on, right? So sometimes the systems aren't set up for that. But at least CUDA is now kind of set up so that you can do frames on time. I don't know about HIP. But so you can use them for game programming. Unfortunately, they're kind of specific, right? And so they're not maybe what you really want, but you can use them. Or at least CUDA you could. I mean, I don't know what you do on Intel. I don't know if that runs CUDA at all, right? Like, I don't know how you would necessarily ship a game that way unless you just had one for each. So it's like, oh, we shipped CUDA on NVIDIA and HIP on AMD and something like that. The Jim James 40, off topic. Do you miss some features that exist in C but are absent in C++? No, because there weren't any of those, really. when I learned C. So no. I mean, there is one, the void star treatment in C++ is really bad. That's the only thing that was true in the original C that they messed up in C++ pretty bad, which is like you kind of got, you were supposed to, you needed a thing that was a pointer that can convert to any other pointer type once, right? So in C, a void star used to mean this could be anything. So if I assign it to a foo star, it will work. C++ failed to introduce, when they got rid of void star as that, they failed to introduce something to take its place. And that was a mistake. So when they first did that change, I do miss that. I wish that was not the case. Let's see here. Thoughts on DXR? I already talked about that in a previous episode. Will you ever get back to the nicely aligned grass rock bitmaps? Not exactly. There is something that will happen there, but I'll save that for a little bit later. But we won't be doing quite exactly that. But we'll be doing something simple. Not simple, similar. Sorry, I could not exactly follow you, but can you guess at what makes the interval computations tiresome? Yeah, I mean, the thing that's the problem with them is that there's too many components to them, right? And this is like a common source of problems and a common source of bugs. And it's because whenever you're dealing with something that has a lot of components, so in this case, we have a minimum and maximum value for the room location, which itself has a minimum and maximum value, each of which is on 3 different dimensions, right? Programming does not make it easy to clearly articulate which of those you're talking about at any given time in a way a brain works. Brains don't think about things in terms of words when those things are non-semantic. Right? So a brain doesn't like think about this in terms of like a min and a max and a radius and whatever, right? It just looks at this and it's like, oh yeah, the cylinder. So the chance that I hand this to somebody else and they don't understand what the bottom and the top are is like 0, right? You have to be a fantastically stupid human being to not immediately know what I'm talking about. On the other hand, when you translate this into code, there are so many variables for all of the parameters here. The width of each of these individual squares and the height of it and which direction they're going and how it's wrapped around here and the fact that the cylinder and the thing are on the opposite sides of this and this thing has a joint level, right, and whatever. When you just look at hundreds of words in code, it's easy to accidentally forget which one of those real world things you're talking about is mapped to the word, because none of them are words you would ever use in daily use. You would never talk about the cylinder that way. You just intuit what it is and you point to it or you do things like that, right? And very rarely do you have to come up with words that specifically locate anything on here other than like top, bottom or something, right? And so that's just a fundamental problem with the way we do programming. And people don't appreciate it. We've known it for a long time, and just nobody bothers to fix it, right? So people spend all their time doing stupid stuff, like arguing over ridiculous things in the C++ standard. If they just deleted 90% of the C++ standard and instead put all of that effort into speccing some visual representation thing you could do with your programming, it would have paid back thousands of times versus anything they've ever done in the language, right? And that's just because they fundamentally don't understand that the hard parts of programming aren't the things that they're looking at, right? Of all the time they've spent looking at things like pointer lifetimes and stuff like that, which are so simple and never really cause problems and are just uninteresting. This is the stuff that's actually hard, right? This is the stuff that's hard for good programmers anyway. Maybe they like to spend their time focusing on stuff that's hard for bad programmers. I don't know, right? But if you actually want to talk about what's hard for everybody, that it's just tends to be difficult. It's things with lots of indices, lots of names, lots of different parts, many dimensions, all these sorts of things. They're just really difficult to program because you just have all of this mapping you're constantly doing in your head. If you ever do one of those mappings in your head wrong, you've got a bug, right? Hopefully it's a bug that shows up, but if you're unlucky, it's not. Do you feel it'd be worth to abstract away subsystems input audio lifecycle with an event system? Well, I mean, I guess I would sort of answer the question with a question, which is, what do you think the bonus of that abstraction? Why? Why would you add events to them? Like, is there something in particular you think you want to achieve? Can we try all the rooms now? No, because they can't possibly be our thing isn't satisfied, isn't smart enough yet to be able to satisfy them, right? And it will just place rooms on top of each other, which will create a huge disaster, right? So if you come in here and actually do this, you're in trouble, right? We've got, first of all, it should just assert that it can't satisfy. Once it gets to a point where it needs to connect two rooms and it can't connect them, it's just going to fail, right? I don't know how many rooms it actually got to, so I guess we can sort of make that happen here. But at some point, right, it's gonna hit that limit. So I don't know what it did. It laid out some rooms here. And hey, they were placed and connected properly, so that's good. But again, it can't. Oh, that's weird. We have too many light points. This must be like a very big room or something. Either that or there's something buggy in there. Let me actually also take a look at this here. But anyway, eventually it shouldn't be able to place some rooms, right? So you can see exactly what it's doing. It's always just going ahead and using the first direction it finds, and it's placing. Eventually it has to place a room which connects back to one of these other rooms, and it can't do it, right? And so it just like fails. What it needs to do is actually be smarter, right? And either try other permutations or have a strategy for actually achieving that. Otherwise, it's just always going to connect them this way, ad infinitum, right? So it's not really at the point yet where we can try to create the world the way we actually want to, and probably won't be for a little while, right? Because we're still just getting into the generative part of it. So two rooms connected to each other is all we can really do at this point in terms of what the algorithm's written for. It's just the basics of that. And then we have to kind of go from there. Jim Zero, have you ever made a visualization tool for working stuff like this out? I'm thinking of something like live code editing combined with showing values on screen and lerping between previous values and new values, showing how the changes affect the scene when the code reloads. Yeah, I would just like that to be part of the programming language though, or part of the debugger, right? I can only dream of that. I have never had time to make one myself. After all of this code on rendering and this, is code reloading still working? Yeah, sure. it depends which code you want to reload, because the stuff that generates the world doesn't get run again. So you can't change that code. I mean, you can change it, but it won't do anything. But the other code you can change just fine. So, you know, for example, if you just didn't want the lighting to run or something like that, you could just say, let's see. Right here inside lighting test, I could just return, right? So here's the lighting running, and I can recompile, and then when it's finished, oh, syntax error. Sorry. When it's finished, how do I convince you to compile? If the compiler ever would produce an actual result, there we go. Then now we're just not outputting any lighting at all, right? And there's just garbage getting output to the textures. And then if I recompile it, right, we're back. So code reloading still works just fine. Garbage or awesomeness. Dev Blackie, are you doing custom memory management? Yes. We do custom memory management. In fact, you will note that in the actual code there are no calls to malloc or new. There's only some in the preprocessor. So nothing with a handmade underscore in front of it is in there. Right. And we have two modes. One of which grows on demand. That's the mode we're using right now. So it actually can't run out of memory unless the system runs out of memory. There's another way we can run it, and we're not really doing that right now, which is where you it's a fixed size, and if you overflow that fixed size, it stops. And that, we haven't really done much with that in a long time. It just kind of is that way. So, all right. So I'm going to go ahead and wrap it up. Thank you, everyone, for joining me for an episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always go to handmadehero.org, and you can pre-order the game, which comes with a lot of source code, so you can play around with it yourself. And yeah, so if you're interested in learning C and stuff, it's a great place to play around with it. That's it for today. I'll be back next week. Same time, same place, probably. But if you're wondering, you can always check the schedule bot. It'll tell you when we're going to be live. Until then, have fun programming, everyone, and I'll see you on the internet.